So today in this lecture we will see the stability analysis of nonlinear systems. So by using phase trajectories. So for linear time invariant system, the concept of stability can be defined as follows. So when the input is 0, the system is stable for arbitrary initial conditions if the resulting trajectory tends to equilibrium state. Second, when the system is excited by a bounded input, the system is stable if system yields bounded output. So the linear autonomous systems has only one equilibrium state and its behavior about the equilibrium state completely determines system behavior. In nonlinear systems, there may be multiple equilibrium states and system behavior at different equilibrium points may be different. Hence, in nonlinear system, the stability is discussed relative to the equilibrium state. Consider an autonomous system described by state equation x dot equal to f of x. Let's assume that the system has one equilibrium point and origin of its plane is the equilibrium point. For this, following definitions of stability are proposed. So first definition, the autonomous system defined by equation x dot equal to f of x is stable at the origin if for every initial state x at t is 0 which is sufficiently close to origin, x of t remains near the origin for all t. Second definition, the autonomous system defined by equation x dot equal to f of x is asymptotically stable if x of t approaches the origin as t tends to infinity. Third definition, the autonomous system defined by equation x dot equal to f of x is asymptotically stable in large if it is asymptotically stable for every initial state regardless of how near or far it is from the origin. Now let us see how the phase trajectories are to be constructed. So construction of phase trajectories. Before going for the analysis methods, let us see what is the phase trajectories or how the phase trajectories are to be constructed. The state equations of a second order autonomous system are given as x1 dot equal to f1 of x1 x2 and x2 dot equal to f2 of x1 x2, that is x1 dot and x2 dot, these are the functions of x1 and x2 where x1 x2 are the state variables of the system. Now dividing equation 2 by 1, we get x2 dot by x1 dot is equal to f2 of x1 x2 divided by f1 of x1 x2. So this is third equation. Since we know that x2 dot means dx2 by dt and x1 dot means dx1 by dt. So equation 3 becomes dx2 by dx1, that is equal to f2 x1 x2 divided by f1 of x1 x2. Let it be equation 4. Now here we can see that equation 4 defines the slope of the trajectory at every point in the phase plane except at the singular point. So at singular point the slope of trajectory is indeterminate. So we will see what are the different methods for the analysis of the nonlinear system. So methods of the analysis. So here we can see that nonlinear systems are difficult to analyze and arriving at general conclusions are tedious. So there are several techniques evolved for the solution of standard nonlinear differential equations. So the different methods are as listed below. So first method is the linearization techniques. Second one is the phase plane analysis. Third one is the describing function analysis, and fourth one is the Lyapunov's method for the stability analysis of the nonlinear control system. So let us see the phase plane method. So this method is applicable for second order linear or nonlinear systems for the study of the nature of phase trajectories near the equilibrium points. The system behavior is qualitatively analyzed along with design of system parameters so as to get the desired response from the system. So this is one of the earliest techniques developed for the study of second order systems, nonlinear systems. It may be noted that in the state space formulation, The state variables chosen are usually the output and its derivative. So the phase plane is thus a state plane where the two state variables are x1 and x2. So two state variables x1 and x2 are analyzed, which may be output variable y and its derivative, that is y dot. This method is used for obtaining graphically a solution of the following two simultaneous equations of an autonomous system. So x1 two state equations are x1 dot equal to f1 of x1 x2, that is x1 dot is the function of x1 x2 and x2 dot is equal to f2 of x1 x2, where x1 dot, that is the function of x1 x2, and x2 dot, that is f2 of x1 x2, are the either linear or non-linear functions of the state variables x1 and x2 respectively. The state plane with coordinate axes x1 and x2 is called as the phase plane. So in phase variable form, the system takes the form x1 dot equal to x2 and x2 dot is equal to f2 of x1 x2. So this method is suited to second order nonlinear systems with no input or constant inputs. Now consider the homogeneous second order system with the differential equation m d2x by dt square plus f dx by dt plus kx equal to 0. So this equation may be represented in standard form as x double dot plus 2 zeta omega n x dot plus omega n square x is equal to 0, where zeta and omega n are the damping factor and undamped natural frequency of the system. Let the state variables are x1 and x2. So let x1 is equal to x and x2 is equal to x1 dot. So state equations will be x1 dot equal to x2 and x2 dot equal to minus 2 zeta omega n x2 minus omega n square x1. So these equations may be solved for phase variables x1 and x2. So the time response plots of x1, x2 for various values of zeta with initial conditions can be plotted. For example, if the spring force is non-linear, say k1x plus k3 x raised to 3, the state equations takes the form x1 dot equal to x2 and x2 dot equal to minus f by m x2 minus k1 by m into x1 minus k2 by m into x1 raised to 3. Solving these equations by integration is not easy task. In such situations, a graphical method known as phase plane method is found useful. So the coordinate plane with axis that corresponds to the dependent variable x1 and x2 is called phase plane. The curve described by state points x1, x2 in the phase plane with respect to time is called as phase trajectory. A phase trajectory can be easily constructed by the graphical techniques. So in phase plane method there are three different methods, that is analytical method, second one is the graphical method which is also called as isocline method, and third one is the delta method. So let us see the isocline method. Let the state equations for a nonlinear system be in the form x1 dot equal to f1 of x1 x2 and x2 dot is equal to f2 of x1 x2, where both f1 of x1 x2 and f2 of x1 x2 are analytic. From above equations, the slope of trajectory is given by dx2 by dx1 is equal to f2 of x1 x2 divided by f1 of x1 x2. So let it be m, that is m is the slope of the trajectory. Therefore the locus of constant slope of the trajectory is given by, that is by cross multiplying f2 of x1 x2 equal to m into f1 of x1 x2. The above equation gives the equation to the family of isoclines. For different values of m, different isoclines can be drawn in phase plane. So knowing the value of m on the given isoclines, it is easy to draw the line segments on each of these isoclines. So consider a simple linear system with states equations x1 dot equal to x2 and x2 dot equal to minus x2 minus x1. Therefore, the slope of the state trajectory in x1 x2 plane is dx2 by dx1 equal to minus x2 minus x1 by x2. So let it be m. For a constant value of slope, say m, we get set of equations as x2 is equal to minus of 1 upon m plus 1 into x1. So which is a straight line in x1 x2 plane. So we can draw different lines in the x1 x2 plane for different values of m and called as isoclines. So let us see the procedure for construction of a phase trajectories. So the following steps are there. First step, for the given nonlinear differential equation, define the state variables as x1 and x2 and obtain the state equations as x1 dot equal to x2 and x2 dot is equal to function of x1 x2. Now second step, determine the equation to the isoclines as dx2 by dx1 that is equal to function of x1 x2 divided by x2, and that is the slope of the isoclines. Then third step, for typical values of m, draw a large number of isoclines in x1 x2 plane. Next step, on each of the isocline, draw small line segments with slope m. And last step, from an initial condition point, draw a trajectory following the line segments with slopes m on each of the isoclines. And we can draw the phase trajectory, that is phase portrait, and from the shape of that phase trajectory we can define the stability of the nonlinear system, that is if it is converging towards the equilibrium point or it is diverging from the equilibrium point, and depending on that the stability of the nonlinear system can be analyzed, or we can state the stability of the system.